Hello everyone. Today we're going to discuss a very important group of functions called exponential functions. As it turns out, many natural and man-made quantities either increase or decrease at an extremely fast rate, and the polynomial expressions that we're familiar with, where the base is a variable and the exponent is a constant, even though they do increase at a significant rate, they don't increase or decrease fast enough to capture the fastest types of natural and man-made growth or decline. What we need to describe that kind of growth is a group of functions called exponential functions, and the difference with them is that the variable, instead of being in the base position like the polynomials we're familiar with, is actually in the exponent position. This minor switch from changing the place of the base and the exponent, like for example from x squared to 2 to the x, is going to create a really large difference in the way that the function grows, as we'll see on the next screen. Okay, so here we have two tables. In one, we're looking at the way the function x squared grows for non-negative values. It's significant, like for example, when x is 0, we have 0, 1, 1, and then it starts taking off pretty well. Like when x is 2, we get 4, 3, 9, 4, 16, 5, 25, etc. We can see that it's growing pretty fast, but now look to the right at what happens when we switch x squared to 2 to the x instead. Now when we look at this function, notice it takes off kind of in a similar manner to x squared does, right? Up to about this point. From here, this one really takes off. Notice like 2 to the 5 is 32, 2 to the 6 is 64, 128. By the time we get to 10, 2 to the x has really left x squared in its dust. So basically, if you think of this as a really good runner, this one is a major sprinter. I mean, there's a huge difference in the way that these two functions grow. So let's go ahead and formally introduce the exponential function. The function f of x equals b to the x for b greater than 0 and b not equal to 1 and all real numbers x is called the exponential function. The domain is going to be all real numbers and the range is all positive real numbers. We'll see why that is in a minute. A couple of points about the restrictions we're placing here. We need b to be positive because we want the exponential function to be well defined for all real values of x. So, for example, if we were to allow b to be -4, for instance, notice that for x equals 1/2, we would get f of 1/2 equals -4 to the 1/2, which is square root of -4, and that is not a real number. So for this not to happen, we went ahead and put the restriction that b should be positive. And of course, the reason we need b not to be 1 is that otherwise we end up with a function like f of x equals 1 to the x, and we know that any power of 1 is just 1 itself. So this would collapse down just to a constant linear function. And we don't want that to happen if it's going to remain a viable exponential function. So that's the reason for those two restrictions. In order to graph exponential functions, we'll basically set up a table of values and plot like with any other function. This f of x equals 2 to the x is often referred to as the reference exponential growth function. Then the reason we emphasize growth is because sometimes exponential functions can describe decline as well. So in this case, we're looking at an exponential growth situation. And if we just pick a few values, like here are the x values, -3, -2, -1, all the way up to 3. we just plug in. So for example, 2 to the power of -3, as we know, is just going to be 1 over 2 cubed, which is 1/8 with by the negative exponent law. For -2, we get 2 to the -2, which is 1 over 2 squared, which is 1/4. -1 gives us a half, etc., all the way up to 8 for y values. So when we plot those points and graph it, we get this really continuous and smooth, extremely fast growing function. And this is with just the base being 2, of course. And now you can see that all x values are in play in giving us the graph of this function, even the ones that are extremely to the right of this point and very large values. Remember, this keeps going, so eventually any x value you pick will have a y value associated with it for this graph. So the domain is all real numbers. Now you can see the values of the outputs, as you can see from the table, even whether you're plugging in negative values for x or positive, they never become negative or even 0. So notice that this curve, even though it looks like it's touching, that's just a limitation of technology, but it actually never crosses the x-axis. So we call the x-axis a horizontal asymptote for this graph, which means this graph will come arbitrarily close to, which is another way of saying as close as you want to get it, basically, to the x-axis, but it will never actually touch or cross the x-axis. Another thing to pay attention to is this point 0,1, which is very interesting given that all these exponential functions, regardless of the value of b, once you raise them to the power of 0, are going to give us 1. So they're all going to go through that particular point. Now let's take a look at what happens if we increase the value of b. See, we're going from 2 to 4 to 10 to 100. Notice what happens basically is that the growth becomes faster and faster. And however, interestingly, notice the domains will all be the same, all set of the set of all real numbers. The ranges for these simple types will also be the same. We'll look at some transformations of these exponential, the basic exponential function later, where the range might change by lifting, etc. But for these, the domain and range all the same. It's helpful to take a look at all the functions we just saw on the previous screen, all put on the same Cartesian coordinate plane. And again, you can see here how they all go through 0, 1, and we can see how the x-axis is a horizontal asymptote for all of them. And what we want to look at now is what needs to happen to b so that this growth suddenly shifts and become a exponential decay, as it's called, situation. Okay, so as it turns out, when the base is like the previous example 2 or any number larger than 1, you end up with an exponential growth scenario. If the base is less than 1, but remember, we can't just leave it there because we want to make sure it remains positive. So we say if the base is between 0 and 1, so we don't want it to go, the base to be smaller than 0, because then it would become negative. And if you recall, we want the base to be positive. So we talk about base values being greater than 1 or between 0 and 1. And never 1, remember, because then it would collapse down to a constant function. So when the base is between 0 and 1, and of course 1/2 is a value between 0 and 1, if you notice, this is exactly what happens. So when you plug in -3, for example, you end up with 1/2 to the -3. And remember, we had a rule that if you have a fraction to a raised to a negative power, you can flip the fraction and change the exponent to a positive one. So we end up with 8. -2 would give us 4. -1 would give us 2. 0 would give us 1, etc. So you see, in this case, the values are decreasing very rapidly. And you can see that beautifully depicted here. Again, x equals the x-axis itself, whose equation is y equals 0, is a horizontal asymptote for this graph. And it behaves very similar to the other one, except in the fact that it is decaying very rapidly rather than growing. The domain and range are once again the same as the previous situations that we already saw. This time we can look at what happened if we decrease the size of the base, keep making it smaller and smaller. We know that 1/4 is smaller than a half, 1/10 is smaller than both, and 1/100th, of course, is smaller than all of them. And notice what happens is that the decay becomes faster and faster as you go from larger base to smaller base in the 0 to 1 category. The domain and ranges do not change because you still define for all real numbers, and you still only get outputs that are greater than 0 in this case. Again, if we take a look at all of those on the same graph, you can see they all still go through 0, 1, and you can see how as we go to smaller and smaller bases, the decline, we should say, becomes faster and faster. These fall faster and faster. Now, sometimes exponential functions are given to us with a negative exponent. So we need to remember these 3 negative exponent rules from our previous experience with exponents, and they're simple enough, but you just need to remember them. If you have x to the -n, that becomes 1 over x to the n. 1 over x to the -n in turn becomes x to the n. And if you have a fraction raised to a negative power, as we saw earlier, you can flip the fraction, reciprocate it, and then change the exponent to a positive value. The same, of course, the opposite of that value. Because of the way that we defined the original exponential function without having a negative exponent, before we can determine whether each of these is an exponential growth or decay function, we want to make sure that we've written the expression of the function using positive exponents. So we're just going from left to right with these 4 functions, and we're going to decide whether they represent exponential growth or decay without graphing, solely based on the values that we see. All right, for the function f1, we can see that clearly the base is 5, which is certainly greater than 1, and there's no negative exponent to deal with, so therefore this is definitely an exponential growth curve. For the second one, we can see that 4/5, which is the base, falls between 0 and 1. Therefore, this would be an example of an exponential decay. For the third function, f3 of x, we need to first write it using positive exponents. So we know that f3 of x equals 3 to the power of -x. And we know that we can write that as 1 over 3 to the x. And in turn, we can go ahead and write that as 1/3 to the x. So the reason this can happen, of course, is because, as you know, if you have x over y, to the n, that's equal to x to the n over y to the n. So of course we can write 1 as 1 to the x. So we're using this rule going from right to left when we go from this step to this step, and we've replaced 1 with 1 to the x. That's why that can happen. All right, so now that we've written it in a form that uses positive exponents, no negatives in the exponent, we can see that the actual base is 1/3. So we make the conclusion that since 1/3 is between 0 and 1, this is going to be an exponential decay curve. You see how important it is to do that, because otherwise you may look at 3 and erroneously assume that, oh, 3 is greater than 1, so this should be exponential growth, which is not the case. Once again, here we notice that we have a negative exponent on the fourth function, so we go ahead and write f4 of x using the rule we saw earlier, that if we have x over y to the negative n, that's the same as y over x to the n. So we notice that we can do that here and say this is equal to 2/3 to the power of x. So once again, we notice that once we do the proper conversion, the 2/3 falls between 0 and 1. Therefore, this is also representing an exponential decay function. All right, if you recalled when we graphed the parabola y equals x squared, which we call the reference parabola, we learned that we can move that graph by changing its equation. Basically, we applied certain changes at the input x level, and that caused certain changes. Then we applied some changes at the entire f of x or y level, and that had other effects. Now we can do exactly the same kind of transformations with y equals b to the x, and we'll take a look at that now on the next screen. These are exactly in line with the kind of transformations we saw in the case of parabolas. For example, if we change the equation of y equals e to the x to y equals 2 to the x minus 3, this is going to have the effect of taking the graph of y equals 2 to the x and moving it 3 units to the right. If you recall, when you change the x to x minus a number, then the shift is actually to the right. If we do the change from y equals 2 to the x to y equals 2 to the x plus 3, that's going to be a shift of 3 units to the left. These are called horizontal translations or shifts. Now, if we bring the change at the entire y or f of x level, meaning we take the entire function and add a number to it or take away from it, that's going to bring a change at the y level. So we're going to be moving it up or down. So for plus 3, of course, we're going to move it up 3 units. For minus 3, we're going to move the graph of y equals to the x down 3 units. When we multiply by a constant like 3 here, we're going to actually bring a change at the y value again. We're tripling the outputs. The output, instead of being 2 to the x, is being 3 to the times 2 to the x. So this is going to be having a vertical stretch effect, of course, by a factor of 3. But remember that when you vertically stretch a function, its graph actually becomes horizontally more compressed, as was the case with x squared that we saw previously. So when this value here is larger than 1, then it is going to have the effect of a vertical stretch, which is simultaneously equivalent to a horizontal compression. When the value here of the constant that you're multiplying by the original function is between 0 and 1, then it's going to have a compression effect vertically, which of course horizontally the graph will get more stretched out. Now, if we have that factor multiplied at the x level instead of at the y level, that's going to have a horizontal effect. Now, with these, you have to be a little bit careful, because when the a is greater than 1, or the constant that you're multiplying here is greater than 1, it actually is going to have a horizontal compression effect, which will appear like a vertical stretch. These always work in opposite manner to each other. And when the constant that you're multiplying the input by is between 0 and 1, that's actually going to have a horizontal stretch effect, which will also appear as a vertical compression simultaneously. The last kind of transformation is the simplest one. That's when you basically just take all the outputs and multiply them by -1. So you're just going to basically vertically flip or reflect the graph. Let's quickly take a look at all these on Desmos for a better, more intuitive understanding. Okay, so here we can see the graph of y equals 2 to the x on the right here. So we'll take a look at y equals 2 to the x minus 3. So let me be lazy and copy that. All right, so if we just change the x to x, this is going to be a little tricky with Desmos. I'm going to have to use parentheses. So x minus 3. And notice that, in fact, let me change the color. It did move the graph 3 units to the right. Now, if we change that -3 to +3, you'll see that the graph of 2 to the x will move to the left 3 units. Now, if we actually change the function to and bring the change like here at the output level, so just add 3 to the 2 to the x itself, notice it's just going to move it up 3 units. And if we of course change that plus to a minus, that'll move the graph down 3 units. All right, so if we look at this vertical stretch example now, we have y equals 3 times 2 to the x. And notice that vertically the graph was stretched. It's as if you're pulling it up vertically by a factor of 3, like the 1 is now 3 as an output. However, when you look at it horizontally, notice that it looks like you actually compressed it, as we were mentioning earlier. These two work simultaneously and they have opposite effects. So if we were to actually, instead of stretching it vertically, if we were to go ahead and multiply by 1/3 instead, notice that the main graph 2 to the x is in red, and you can see the blue one has been vertically compressed. But when you look at it horizontally, notice it looks like you actually stretched it horizontally. So a vertical stretch and a horizontal compression go hand in hand. All right, so next, let's go ahead and look at the horizontal dilation. And here we're going to change 2 to the x to 2 to the 3x. Well, we're going to look at both. So, okay. So, remember we said that when it comes to horizontal compression or dilation, when this factor is actually larger than 1, it actually has the horizontal compression effect. And notice horizontal compression goes hand in hand with actual vertical stretching. Now, if that 3 is changed to 1/3, oh, not that. Let's see, 1/3. No, let's get rid of that. Notice that's going to have the effect of a horizontal stretch, which vertically, of course, it will look like a compression. See, it looks like it was vertically compressed. And once again, they go hand in hand. Finally, we'll take a look at the reflection. That's when we just look at y equals, we just multiply it by -1, so it becomes -2 to the x. And see, that one just flips it vertically. So that's called a reflection. All right, those are the various types of transformation you can apply to the exponential function. Okay, by now we have seen these kinds of transformations with both parabolas and exponential functions. But the nice thing about it is that what you have learned applies to all functions. So we can generalize this on the next screen. So in general, if you have a function f, and assuming that you know the graph of the function f of x, and if you choose some k value greater than 0, if then you want to obtain the graph of f of x minus k, you're simply going to shift the graph of f k units to the right. With x plus k, you're going to shift the graph k units to the left. If you have f of x plus k, you're going to shift it up k units. With f of x minus k, you're going to shift it down k units. Now, when you multiply f of x by k, you're going to vertically stretch if k is greater than 1. You're going to vertically compress if k is between 0 and 1. And of course, remember, every vertical stretch is simultaneously accompanied by a horizontal compression, and every vertical compression is simultaneously coupled with a horizontal stretch. For when you want to do a horizontal compression, you bring the change about by multiplying the k by the input x, and that of course will be coupled with a vertical stretch, and that's for k greater than 1. When k is between 0 and 1 and you multiply it by the input x, you're going to get a horizontal stretch, which is a simultaneous vertical compression effect. And of course, if you just simply want to flip the graph of a function, just multiply it by -1. Next, we're going to try to solve some exponential equations. We'll be looking at the simplest type in this section. These do not require the utilization of a function called a logarithmic function, or also a concept called the concept of logarithms. We can do these by just basic rules that we'll discuss in a second. The game plan is basically going to be this. We're going to deal with equations where this scenario is possible for them. That means we're going to be looking at exponential equations where it is possible to write the two sides using the same base. Once we have done that, because we know that the exponential function is 1-to-1, let's take a look at its graph real quickly. If you remember the graph of the exponential function which we saw earlier, clearly it passes the vertical line test, so it's most definitely a function. But notice it also passes the horizontal line test. You're not going to get any horizontal line crossing it more than once either. Because notice in this region, you may be thinking, oh, it looks like a horizontal line will cross it there. But no, there is always some angle here which is going to make every horizontal line cross it only once. Now, what's the significance of that? The significance is that if you have two outputs that are equal, that means they must have come from the same input. Because remember, with one-to-one functions, no two inputs have the same output. So if you have two values of b to the x that are equal, and then the inputs must have been the same. Let's go back to the equation we were looking at a minute ago. So if these two outputs are the same, that means the inputs x and y must have been the same because of one-to-oneness. We're going to be using this fact to solve certain types of equations where this becomes possible. Next. All right, so here we have an equation, 9 to the x equals 243. We're going to try to write both sides of this equation as powers, but with the same base. Now, it does look like we should be able to use the base 3 at the very least. So we are going to go ahead and look at the prime factorization of 243 to see what it looks like. Now we know that 3 goes into that 81 times. 3 again goes into it 27 times. 3 again 9 times. Remember, on the left side you only want prime numbers if you're going to obtain the prime factorization. 3 again will give us 3, and then one more 3 will give us 1. So it is 243 is definitely a power of 3. In fact, we know that now we can write it as 3 to the 5. But notice it is not a power of 9, because you have one 9 here and another here, but you don't have another one. So it's not a power of 9, but it is a power of 3. So we're going to go ahead and write both sides as powers of 3, because we already know that we can write 9 as a power of 3. So we'll go ahead and write 9 as 3 squared to the x, like that, and we'll go ahead and replace the 243 with what we now know to be 3 to the 5. So of course now we'll use the power rule to simplify the left side down to 3 to the 2x. And on the right side we have 3 to the 5. Now we have the form that we're looking for. We want b to the x equals b to the y, so that we can from there conclude that x must be equal to y. So at this point we go ahead and say therefore, and this is, again, if you want to give the reason, it's by one-to-oneness of the exponential function 3 to the x. F of x equals 3 to the x, so we get 2x must be equal to 5. Be very careful here. This is not a simple dividing both sides by a number or multiplying by a number. It's not a basic operation. This is a complex deduction based on a complex understanding of the one-to-one nature of functions. So make sure you're not experiencing the error of thinking we're canceling the 3's or anything like that. That is not what's going on here. So then finally we just get x equals 5 over 2. And that should be it. Now it's easy to check the answers. You can just plug into the original equation 9 to the 5/2, see that if that gives you 243, and of course that's going to be the fifth, actually the square root of 9 to the 5. You want to know if that's 243. Remember, we have a nice rule that says if you have the nth root of x to the m, you can take the nth root of x first and then raise it to the power of m. That's going to help us here because we're going to take the square root of 9 first and then raise it to the power of 5. See if that's going to give us 243. And of course, square root of 9 is 3. We want to know if 3 to the 5 is 243. And if you notice, we verify that here. So at this point, our next line is going to be 243 equals 243 with no more question mark needed because we have verified it. So now we can write the solution set professionally as solution set contains 5 halves. Just wanted to demonstrate that for you. We won't be taking the time to check every one of these because otherwise the video will go on forever. But you should definitely do that for yourself. That's always good practice with radicals and similar skills as well. Okay, so here we have another one of these, and of course, if you recall when we did a video on powers, I gave some tables out for you to memorize, because being familiar with these powers, at least for each table, like for example for squares, you'll want to know probably up to 12 or 13. But for the rest of them, you should know at least the first 4 or 5 powers. Like say for cubes, you should know cubes up to like 5 cubed. You should know fourth powers up to probably 5 to the 4, etc. So this will make you very sharp with this kind of problem, and also it'll help you recognize the bases that you're going to need. Here, I think it's pretty clear that we're going to need to use the base 5. So we'll go ahead and write 25 as 5 squared to the x, and we'll write 125 as 5 cubed. Of course, you know 125 breaks down with 5 giving you 25, another 5 giving you 5, and one last 5 giving you 1. So 125 is the same as 5 cubed. So we get 5 to the power of, let's not forget the x plus 5 here. Okay, so we get 5 to the 2x equals, now that 3 and the x to the 5 need to be multiplied. Of course, we're using the rule that says x to the m to the n equals x to the mn, also known as power rule. So we get 3 times x plus 5. Now we have the scenario we wanted. We have 2 powers here. They have the same base, so b to the x equals b to the y. We're going to deduce that x must be the same as y. So now we can say 2x equals 3 times x plus 5. So now we just have to solve that simple equation, which is linear. So we get 2x equals 3x plus 15. Let's go ahead and move the x's to the right side to get 3x minus 2x. We'll move 15 to the other side, becomes negative 15. So we get x equals negative 15. And that is the number that's going to do the trick here. Now, of course, with an answer like this, checking by hand would not be the simplest thing in the world. So you can always bring up a calculator and check using a calculator. So let's do that. All right, so here what we'll do is we'll go ahead and type 25 to the power of x, which is negative 15. That's our proposed solution. And we'll go ahead and hit enter to get a value. Now that's a very, very small number, as you know. So now what we'll do is we'll go ahead and compute the right side, which is 125 to the power of x plus 5. So negative 15 plus 5. And we notice that we get exactly the same thing. So we know we have done it correctly. We go ahead and write the solution set. When you write the solution set, don't bring the x, just the numerical value of the particular x value that works. And that's how you do a problem like that. Make sure that every single one of these, if we're done, if you didn't get it on your own already, that you do it on your own and make sure that you can comfortably go through all the steps. Don't come and unpause and go to the next problem until you do, because otherwise optimal learning is not taking place. And of course, it goes without saying that as soon as you do see a new problem, you should definitely pause the video and try it on your own before you come back to watch the rest. All right, so here we can see that 2 is a good candidate for our base on both sides. So we'll go ahead and write the 8 as 2 cubed, and we're going to raise that to the power of 3x minus 4. And we're going to write the 16 as 2 to the 4. And of course, we need to raise that to the power of 2x plus 3. All we did was replace 8 with 2 cubed and 16 with 2 to the x plus, with 2 to the 4. All right, so we get 2 to the power of 3 times 3x minus 4 equals 2 to the power of 4 times 2x plus 3. So we get 2 to the power of 9x minus 12 equals 2 to the power of 8x plus 12. So now we're going to go ahead and set those equal to each other, those two exponents, because of the one-to-one nature of the exponential function. So we get 9x minus 12 equals 8x plus 12. So if we move the x's to the left side, we get 9x minus 8x equals 12 plus 12. So we get x equals 24. All right. So let's go ahead and run a quick check on it, make sure that it works so that we didn't make any quick errors. So we'll go ahead and remember, you always want to check in the original equation. So we're going to go ahead and type 8 to the power of 3 times 24. We're replacing x in the original equation with 24. And we go ahead and subtract 4. So that's 3 times x minus 4. And we get this value. This time that's a huge number. And now we're going to go ahead and type evaluate the right side, which is 16 to the power of, okay, we need to do the power. So to the power of 2 times 24 plus 3. And we go ahead and hit enter and hope that we get the same thing. Of course we did, so we're good to go on that one. All right, so now we're going to write our solution set, which is going to contain 24. As always, make sure you can do it on your own before we proceed. All right, so for this next one, give it a try, see what happens, and then come back. All right, welcome back. If you're familiar enough with powers, you should recognize both 8 and 128 as powers of 2. 8, of course, we know is 2 cubed, and 128, if you just do a quick prime factorization, you get 2, 64, 2, 32, 2, 16, 2, 8, 2, 4, 2, 2, 2, 1. So you can see there is 1, 2, 3, 4, 5, 6, 7. So 128 is the same as 2 to the 7. So we're going to go ahead and write the 8 as 2 cubed like this. We need the x on the outside as a power, or the exponent, and down on the other side we're going to write 1 over 2 to the 7. So we get 2 to the 3x. All right, we certainly don't want to leave this 2 to the 7 down here because we want to have the same base, and this is not going to cut it. So we're going to use this rule, 1 over x to the n equals x to the negative n, to go ahead and bring that 2 up. So that becomes 2 to the negative 7. Now we have the form that we want. So now we're going to go ahead and conclude that therefore 3x must be equal to -7. So we get x equals -7/3, like so. All right, let's go ahead and do a manual check on this one. We want to know if 8 to the power of -7/3 is equal to 1/128. So, of course, we know that 8 to the -7/3 is the same as 1/8 to the 7/3. We want to know if that's equal to 1/128. So we know that that can be written as 1/3 to the 7, and we want to know if that's the same as 1/128. And we know the nice rule that tells us it's okay to take the cube root first and then raise to the power of 7. That really makes calculations much simpler. And continuing on the right, we know that the cube root of 8 is 2. So now we're down to this. Is 1/2 to the 7 the same as 1/128? Well, if you know this, we've already shown that 2 to the 7 is 128. So finally we get 1/128 equals 1/128. We no longer need a question mark because we have verified. We did need it over there. All right, so at this point, make sure you keep question marks until the last step where you either show that they're equal or that they're not. In either case, you can drop the question mark because by then you know. But until then, you're verifying, you're not asserting, so you do need the question marks. All right, so that's that, and we'll go ahead and write the solution set. We have one solution, and that is -7/3. All right, so make sure you try that before we move on. All right, this is actually going to be our last one, so definitely give it a shot, see if you can get it on your own, and then come back. All right, so 125, I know that is a power of 5, right? 5 cubed. 216, I know what it is, you may not. So let's look at the prime factorization. This is the good news. Even if you don't know these things, if you take the time and find the prime factorization, you can always find it. So 2 gives us 108, 2 gives us 54, another 2, 27. Now we go to 3, which gives us 9, 3 again, 3, and finally one last 3 gives us 1. Now we notice these nice pairings of 3 6s, right? So you can see that 216 is the same as 6 cubed. So we have 5 cubed down on the bottom of that fraction, and we have 6 cubed on the top. So let's start with that, see where we can take it. So we have 5/6 to the x equals 6/5 cubed. Now, that's almost what we like, right? We actually want to have the exact same base. So one of these has got to change itself. And how? Well, remember, we have a nice rule that if you have x/y to the -n, that's equal to y/x to the n. You always have to learn mathematics formulas left to right as well as right to left. Some people only learn it in one direction and then they won't know how to apply it when it needs to go the other way. So one useful way of doing that is to actually write it from right to left with the right side on the left, in case your mind just likes to function that way. This way you compensate for that. So I just wrote the exact same equation. I just wrote this side on this side, and I wrote the left side on the right side. So you see, you should be able to apply this. Now, I can do it to the left side or the right side, but usually I like to leave the x alone. Don't turn it into a negative x, so we'll do it to this side. So we go 5/6 to the power of x equals 5/6 to the power of -3. Now we have the exact same base on both sides, so we can say therefore x equals -3. And checking this is actually very fast, so let's go ahead and do it. We want to know if 5/6 to the -3 is the same as 216 over 125. Now, of course, 5/6 to the -3 we just learned is the same from this rule. Now we're going to go from left to right. We know that it's going to be the same as 6/5 cubed. We want to know if that's the same as 216 over 125. Of course, we know what 6 cubed is because we worked it up up here. So we have 216, and we know that 5 cubed is 125. So we get 216 over 125 equals 216 over 125. We no longer need the question mark. It has been verified. So now we can confidently say the solution set contains the x value -3. All right, and that basically brings us to the end of this video, and I hope you learned a lot and that you will practice many of these so that you can comfortably master these. As you move on to higher levels of mathematics or to other classes, these are going to be the tools you're going to be using all the time. You have to really master these. So, all right, be safe until our next video.